And then on our final talk in the session, we have Leonard Truong, who is going to be talking about Latte, which is a DSL for specifying and optimizing neural networks, so in the context of deep learning.
How's the volume? Good? Okay. All right, so thank you for the introduction. Yes, so I'm here. This is some joint work that was done while I was an undergraduate at UC Berkeley and also an intern at Intel Labs. Here's a list of some of the collaborators involved. So we built Latte. It's a language compiler and runtime for deep neural networks. So this talk will cover a little bit of background really quickly to get people up to speed who might not know that much about deep neural networks. And then we'll dive deep into the Latte system, go over all the internals and the evaluation. So I originally had this slide that talked about how deep learning research is thriving. Thanks to that keynote this morning, we don't have to go through it. The good thing to know, though, is that deep neural networks are getting good at playing board games. We can beat humans, and that's always nice. So Deep Learning 101. 2 slides. We're going to talk about some key terminology that I'll use in this presentation. And hopefully this will cover enough for you to know exactly what we're talking about later on. So neural networks, they're a family of biologically inspired, I use that loosely. Some biologists don't really like this, but it's biologically inspired machine learning models. They look like this on the bottom. It's a graph of neurons, and these neurons are typically organized into layers. So you don't just have a hodgepodge of neurons in free form flowing. We'll group them into groups. You'll hear this term architecture or model. They're used interchangeably. And basically this means a specific configuration of layers. So when I talk about a certain architecture, I'm talking about a way that we've hooked up certain types of layers together. And sort of what are these neurons doing? So these neurons could do things in general, but the most common example of what you'll see, and sort of what's taught first in neural network classes, is the idea of a weighted neuron. A weighted neuron takes in an arbitrary number of inputs. Here we have 3. It'll multiply each input value by some weight, and it'll also add a bias term at the end. So a key thing here is that the weights W1, 2, and 3, and also the bias B, will be learned. So these values will change as the neural network sees more training examples. So to train a neural network, it's a pretty simple process. So you say for each training sample, I'm going to do what's called forward propagation. So that will feed the values forward through this network. Then you'll compute some costs. You'll figure out based on your training example and your training label, was the network right or was it wrong? And then we'll initialize this space called backpropagation, which will distribute gradients to each neuron. The intuition as to why this is needed is this basically tells each neuron how it contributed to the end result and what it needs to change internally. And once it has that information, these neurons can all update their internal parameters. So an important thing is that this process will go over the training data set multiple times. So once you see one training example, you might want to come back and try it again after you've done some more learning. So now that you know a little bit about deep learning, we'll talk a bit about deep learning research. So first I want to pose a question. What's the best programming environment for deep learning research? What should they be using? How should they be programming their systems? And to answer this, we can look at sort of a history of deep learning advancement. So this is a really incomplete list. But what we have here is on the top, we have papers that were published about new layers. So before I was talking about layers, these papers introduced a new layer that did some new function and it advanced the state of the art in some way. And on the bottom in the green, we actually have new network architectures, so new ways to configure existing layers. And they also advance the state of the art on certain tasks. So what we can see is that deep learning research is really just driven by the ability to come up with these new layers and these new architectures, but also the ability to evaluate them. So once you've got an idea based on whatever you've been thinking about, you need to test it on some training data and evaluate how it's going to do. So the problem is, this can take days to weeks. So two examples, AlBassam, which was sort of a famous rebirth of convolutional neural networks in 2012. They reported it took 5 to 6 days for them to train on their GPUs. V2G, a model that's a little more recent than AlBassam, it actually took 2 to 3 weeks to train. So you can see this is sort of a big problem. If you have a new idea, you have to come back 2 to 3 weeks later, and hopefully it's better than your old idea. So first, I'll walk through this graph on the right. We're going to go over sort of the existing deep learning software landscape, what the existing solutions have been. So on the x-axis here, we have productivity. So as we go to the right, we have solutions that might be more productive, easier to program. And on the y-axis, we have performance. So as we go up, these solutions will be better performing and be able to evaluate faster. So the first example of software or a methodology for providing deep learning software is this idea of, or what we'll call a layer-specific library. So they're pretty simple. They provide a function to perform the computation for a layer. You could think of it similar to BLAS for linear algebra. You want to do some layer in the middle of your network, you get a function to do that. This is great because then you can go implement these functions really efficiently, just like BLAS. So cuDNN you could think of sort of as NVIDIA's version of BLAS for deep neural networks. But there's two problems here. The first is it's hard to program. So we can see that it's pretty low on the productivity axis. And the reason is you usually have to know a really low-level programming language. And on top of that, you need to have deep knowledge of the target hardware that you're writing code for. So if it's a GPU, you have to really understand the architecture and optimize it to death. And then another key point here in bold at the bottom is that these layer-specific libraries can't perform fusion across layers. What that means is that each layer function is static and compiled ahead of time. So this means once you know at runtime what configuration of layers that you have, you can't perform any optimizations because your kernels have already been compiled. So another approach that has recently gained a lot of popularity is this notion of a computational graph engine. So someone had the insight that deep neural networks are really, they could just be expressed as a graph of general operations. A node in this graph would be a computation, and an edge is a data dependency. The most famous example of this would probably be TensorFlow. I think Theano was sort of one of the first ones to really get popular and is still used a lot in this space today. So the benefit is that these are easier to program. They raise the abstraction level a bit. But this usually comes at a cost. And what they do is they sacrifice performance. And the way that I'll motivate that statement is that most of these computational graph engines actually provide bindings to these layer-specific libraries. And the reason is that for certain layers, they're just too expensive to be computed with this high-level system. They need to drop down into a layer-specific library to really be competitive in this space. And because of that, then, that they're subject to all the same faults in these layer-specific libraries. So it's pretty simple. The idea is that we have this trade-off between performance and productivity in this existing space. And we'd really like to have our cake and eat it. We want to be productive, and we also want to be performant. So introducing Latte, the system we built, the first component is a domain-specific language. It allows you to describe deep neural nets as a system of interconnected neurons. This language was designed to be at a high level and match domain concepts. We built a compiler. It constructs an implicit data flow graph in the user description. So if you remember back to that picture of a deep neural network, it kind of looks like a data flow graph, and it really is a data flow graph. So our compiler constructs that, and then it synthesizes an implementation of that data flow graph. It performs some optimizations. And then we have a runtime. So training deep neural networks is inherently data parallel. It's pretty simple data parallelism. But a key thing is that any real-world deep learning system needs to support distributed memory parallelism. These networks take so long to train that if you can't do that, you're sort of dead in the water on arrival. And then I'll demonstrate competitive performance. So we got 3 to 6x speed up over Caffe, which is a C++ implementation of a deep learning framework. And we'll go over that in the evaluation section. So high-level overview of the Latte system. It begins with this Julia embedded DSL frontend. So if you're not familiar with Julia, it's a relatively new technical computing language. Its syntax is pretty similar to MATLAB. One key difference is that it introduces an optional type system. And this is pretty important for them to be able to get this high performance that is sort of their main selling point. So the Latte DSL really boils down to 3 main language constructs. We have the notion of a neuron and a connection, shown here as circles and edges. And then we have the notion of an ensemble. So an ensemble here is just a group of neurons. The way this relates to layers, as I defined earlier in Deep Learning 101, is a layer is really an ensemble of neurons plus a specific set of connections. So the neuron in Latte is a primitive abstract data type. It has 4 default values. It has a value, which represents the output value of the neuron. It has a gradient, which represents the gradient for this neuron. And then it also has the 2 fields inputs and the gradient of the inputs. And what this is it's a vector in Julia, which is a one-dimensional array. And it points to the value and the gradient of all the connected neurons. So an important thing is when implementing a neuron, the user can define additional fields for internal state. This is entirely optional, so certain neurons that you find in deep learning won't need any additional state. But the user must implement a forward and a backward function. So the user has to define what happens during forward propagation for this neuron and what happens during backward propagation. So as an example, we'll take that weighted neuron that I described in Deep Learning 101. So we first need to define a couple additional fields that we'll need. So the first one is for the weights and the gradient of the weights. So the weights are what we'll use to scale our input values. And the gradient of the weights will store how we're going to update the weights during backpropagation. We also have the bias and the gradient for the bias because that's another parameter that we'll be learning during the training phase. So it's important to note here that we don't actually define value and gradient and also inputs and gradient of inputs, and that's because it gets inherited. So this isn't sort of, or this macro that you see, this @neuron on the top left, will actually define those fields for you. It's sort of implicit because Julia doesn't actually have inheritance. So to implement the forward propagation of weighted neuron, it's pretty simple. It looks almost like a dot product. So you'll say for each input, you're going to scale it by a weight and accumulate it into your current neuron's value. And then you'll also, at the end, after that, add the bias. So the idea here is that this neuron type is really supposed to match what you're thinking about when you're constructing these neural networks at a very high level. The important thing is that we've actually separated the concerns of computation here from data flow. So this definition of neuron forward doesn't actually make any assumptions about where our inputs are coming from. We've sort of abstractly defined a function based on any number of inputs. We'll show you how to actually specify the inputs when we talk about connections later. So an ensemble is really just an n-dimensional array of a neuron of a specific type. So every neuron in an ensemble should be of the same type. And connections are defined by a mapping function. So a mapping function takes in the index of a neuron in the sync ensemble, so the destination ensemble. And the mapping function should return a range of indices in the source ensemble that it wants that neuron to be connected to. So to illustrate this, we have neuron indices on the neurons. So we can imagine for neuron at index 1, we're going to return this range 1 to 2. And what that does is that hooks up neurons 1 to 2 to neuron 1. And then again, we do this for all the other neurons. So to put it all together, we're going to implement a fully connected layer in Latte. So it uses that weighted neuron definition that we talked about earlier. And a fully connected layer will instantiate a new ensemble and connect every neuron in the input to every neuron in the output. So the first thing we do here is we create a 1D array of weighted neurons. And then we apply a connection scheme where we say, given our index, we're just going to return the entire range. So this example is sort of, I thought, a very good example of showing how Latte is really at a high level. We're talking about building this graph of neurons and connections, and we're not really thinking at all about how this is going to be implemented under the hood. This process that we're about to talk about in the compiler is sort of what people have to do by hand nowadays. They have to go from this representation and come up with a clever way to implement it efficiently on their existing hardware. So the Latte compiler will consume the results of this DSL front end, which is actually a data flow graph. It'll perform synthesis, do some optimizations, and then generate code for the target hardware. So I talked about this briefly. The user is implicitly describing a data flow graph. So we have this similar looking graph here of neurons and connections, but really what it is computation and data dependence. Internally, we're actually storing this implicitly, so we don't actually construct this graph because some networks might have millions or billions of connections and neurons. So instead, the mapping function can encode this data flow graph, and we can have access to certain parts of it when it's needed. And another thing is ensembles provide a natural partitioning of this data flow graph. So instead of just having one giant graph of tasks and connections, we already have been given a way to partition the graph by the user. So the first thing our compiler does is it synthesizes code to prepare the inputs for each neuron. So based on our connection scheme, you might be able to see, if you're close to the front here, certain neurons are connected, these neurons are fully connected. So these neurons are fully connected, but that doesn't have to be the case. They can be sparse connections. So in this context, Latte will actually copy the input values so that they're contiguous and prepare the data. And that way, the forward function that you saw will just assume that it has a 1D vector of inputs. And then after that's done, Latte will synthesize code to perform the actual computation. So this involves some program transformations. It takes your forward definition and actually generates code that will execute that forward function properly. And then I'll touch on this. We also synthesize code for distributed memory communication. So when you're doing data parallel training, there's opportunities to overlap computation with communication over the network. What the Latte compiler will do is it will synthesize code to do this synchronization whenever the data is ready, and this allows you to overlap that communication over the network with the rest of backpropagation. So for compiler optimizations, the most important one, which I'll cover in this talk, is cross-layer fusion. The idea here is that when you have the kernels for certain layers, you can use information in the dependence graph to perform fusion of loops to perform fusion of loops. So I'll reiterate that this is something that can't be done in sort of the traditional approaches. One, because they use static libraries, and two, because it can be difficult to get this dependence information. But for us, we're lucky because the user has already provided it. There's also a couple other ones that we won't go over, but you can read the paper to look at. We do shared variable optimization. So neural networks, a common pattern is for variables to be shared amongst neurons. In a fully connected layer, for example, all the neurons in the output share the same vector of input neurons. We also do library kernel pattern matching. So A lot of stuff in deep learning looks like matrix multiplication, so we'll look for stuff that looks like matrix multiplication and replace it with a call to MKL. And then we also do general loop optimizations like tiling and fusion, but another key point is that we use this dependence information that we already have, so these optimizations can skip those analysis passes and leverage that language design. So an example of cross-layer fusion, you don't have to read this code, but I'll point out some important things. So on the left, we have a key that shows what code belongs to what layer. So we have 3 different layers, and they're generated code here. So these loops in red, you'll see that these 2 might be easily fused because they're of the same length. This might be a little more tricky because the loops are of different lengths. And then here we have a possible fusion-preventing dependency, and the reason is that we have a non-zero dependence distance on this access, on this read over here that was written in the previous loop. So luckily for us, this might be something that you could figure out with some sort of smart compiler analysis, but we already have all this information, so we can fuse these loops. And the way you do it is you have to unroll the previous loop, and that'll handle the differing loop lengths. So again, this is a key takeaway is that static libraries can't do this. So this enables performance that static libraries aren't able to take care of. In contrasting with computational graph engines, we already have all this dependence information. A traditional graph engine might be able to do this, but it's going to have to do complicated analysis to figure it out. And from what I understand of the state today, none of the graph engines are doing this internally. So I'll briefly talk about our parallel runtime. I talked a bit about how we wanted to overlap this communication with computation. So the runtime is responsible for doing this overlap communication. Here we have a sort of diagram of what data parallel training might look like. We're going to replicate our network across however many nodes we have. And then our runtime is responsible for coordinating amongst these nodes to make sure that they're synchronizing their computed gradients. And then we also support automatic offloading to accelerators like the Xeon Phi. There's usually a cost associated with moving data to the accelerator and then copying the output back. So what our runtime does is it will actually overlap computation on the host while this is happening. And this will hide the cost of data transfer to and from, and that will just get increased throughput overall. So evaluating Latte, we compared the performance against some open source frameworks. In this paper, we'll talk about Caffe. You can see, or in this presentation, we'll talk about Caffe. You can see more results in the paper. We focused on training throughput, as this is the time it takes for developers to iterate on their designs. And in this talk, we'll cover our single node performance and our performance on the Cori supercomputer. For more platforms like Xeon plus Xeon Phi and a commodity cluster, you can see the paper. So for the single node evaluation, we took 3 of the winners of the ImageNet Challenge, which was a computer vision challenge. This is from 2012, 13, and 14. These are the 3 network architectures that got the best performance on the task of classifying images. And we see that we got a 3 to 6x speed up over Caffe for training. So this is great. We lifted our abstraction level above Caffe. We provided a productive abstraction, but we also got better performance on 3 sort of very different models. So to understand the breakdown of how these optimizations that we did affected our performance, we took the first 3 layers of the VGG network, and then we measured our performance with different optimizations turned on. So with just parallelization in our code generation scheme, we see that we're already beating Caffe by a good margin on these first 3 layers. Tiling helps us out, but more importantly, enabling fusion across these 3 layers gives us a huge performance boost, sort of motivating this ability to dynamically do this fusion at runtime instead of going with this old static library approach. Similar to the last graph, this looks at sort of these groups of layers. So on the right, we have a list of layers in the VGG network. we grouped them into groups of layers, and the idea here was that we could see how important fusion was. We see that as we go down through the network, the problem size is actually decreasing, so our optimizations are less beneficial. The reason is we're both using MKL, and we're both spending similar amounts of time inside MKL, so our other optimizations are less apparent. And then for distributed memory, we measured our scaling efficiency, so we get pretty good scaling. The way this was measured is, or the way this was evaluated is that we started with a batch size of 512 training samples. We gave each node a subset of those samples. So as we increase the number of nodes, the amount of work on each node reduces, and we see that as that amount of work gets smaller and smaller, our implementation is less efficient. So in conclusion, we developed a novel abstraction for describing neural networks. It's very high level and matches the domain concepts. And we hope that this will enable productive experimentation of new layers. Importantly, we demonstrated competitive performance with existing frameworks. So, developing a novel abstraction in the space isn't really that cool unless you can at least allow people to train in a similar amount of time with their existing solutions. Our code is available on GitHub. You can check it out, intellabs/latte.jl. And I'll briefly mention that we have a lot of ongoing work. We have a forthcoming release of Latte in Python, and this has some new features and better performance. Come talk to me if you're interested in that. And I'd like to acknowledge a bunch of people that were involved, aside from the authors, for all their great advice and feedback.
If you have any questions, please comment. Hi, great talk. So most of the training nowadays in the field of deep learning is done in GPUs as an underlying platform. Have you done experiments on that architecture?
So we have not. I will say that our techniques are sort of not dependent on the target architecture. So there's no reason that what we did couldn't be applied to GPUs. The reason we chose the Xeon system for our signal node performance was that we wanted to target something like the Cori supercomputer, where distributed training was more important than single node performance. And you'll see that in a lot of existing solutions, they're bound by communication time rather than their ability to process on a single node.
Thank you.
So my understanding is TensorFlow actually does some of the dynamic optimizations that you mentioned as well. So have you guys compared that?
Yeah, so the simple answer is that on a single node, Caffe is still faster than TensorFlow. So implicitly, that there's a performance improvement there. Comparing to, so TensorFlow's optimizations, from what I understand, can do things like, if you have an element-wise operation, you can compute them in place or perform a fusion of that. So that's something that we definitely will be looking into. There's been a lot of talk about TensorFlow, and it actually was published after we published this original paper back in November, or we submitted the paper. So in our following up evaluations, we'll definitely have them as a benchmark.
So I actually take a look at the paper before the talk, and there was one section that mentioned about that the user also have to implement the backward gradient calculation that you actually haven't talked in the presentation. But I wonder why, because I seen in other framework, they actually have techniques to do that automatically, and why do you choose the user to actually implement those parts?
Yeah, so that's a great question. Something that has come up before, and there's no reason why we can't. We wanted to get to the performance comparison, and it's easier to implement backwards than have it automatically generated. There is still one reason why you might want to be able to implement backward by hand, and that's certain operations in your neural network aren't differentiable, but we have a way to do backpropagation that can sort of emulate that differentiation. So for example, max pooling You aren't actually doing the derivative of max pooling to implement the backwards function, but we have an implementation of backwards that we use in practice.
I have a question about, so this is for convolution nets mostly, right? So if you do like recurrent nets, or
Yeah.
variants,
No, so it's not mainly for convolutional neural nets. The idea was that we could implement general neural networks that could be expressed as any arbitrary neurons in a set of connections.
But if you have something like recurrent nets, LSTMs, right, the structure is
Yeah.
very repetitive structure, right?
So we covered that in the paper. I didn't cover it in the talk, but we do support recurrent neural networks. And the idea is that you're just unrolling the graph in time. So sort of everything here holds after you do that unrolling.
Another question I had is that this data flow approach, kind of capturing the data flow, right? There's lots of transformations people have looked at. I mean, in compiler optimizations on data flow graphs, dependence graphs, and so on. And some of the ones you showed are fairly standard optimization, but some are specific to the. Which ones exactly were specific to the domain of neural nets here, of the transformations?
So I think the transformations are not. So there are specific transformations. One that could be used in general. I don't know how useful they would be. Is this idea of sharing certain inputs? So a very common pattern in this data flow graph is that a lot of computation nodes will have overlap input values. And knowing that information can allow you to schedule that sort of implicitly very, very well. But sort of the key wasn't necessarily that, or the key was that this data flow graph was built implicitly by the user. So, we didn't have to go through a step where we had to construct it based on some program where we might not know what's going on with it.
All right, let's thank Leonard for that talk. And that is it for the